SwayamPrabha. Digital India. Educated India.
Hi, welcome back. So we have studied the round jet in detail, right? And we saw that there are several parameters that describe such a in a case of a turbulent flow. And we also found that self-similarity exists, for certain parameters and the way we bunch them up, right? And that kind of gives us a little more understanding of the turbulent properties of such a case, right? So we've done the round jet in a lot of detail. We've kind of touched upon that there are other similar flows like that, right? So similar in the sense self-similar flows like that, okay? So I did touch upon this earlier. So I thought I'm going to do a little more in detail and show you some plots and see how that works. Okay, so you've seen plots, experimental plots, and numerical results for the round jet. So now we're going to consider, well, let's just say that self-similar flows, right? We're talking about self-similar flows other than the round jet, right? So, well, some of the examples of the classical free shear flows are, so is the plane jet, okay, a mixing layer, okay, and the plane and axisymmetric wakes, okay. So let's just do that. So I'm going to start with the plane jet, okay. So I'm going to start with the plane jet, okay. So this is something that we've touched upon earlier. So you might sort of remember or find some similarity at least. Okay, so okay, so you actually have the jet coming out, right? Okay. Okay, so this height is actually d. Okay, then let's draw an axis system such that, so this is essentially x, this is the y, okay, and this there is a certain characteristic length which we call as delta, okay. So I'll come to UC and US in just a bit, okay. So yeah, I think I will come to this in just about a bit. Okay, let me explain a few things here and then I'll go ahead and explain that. Okay. All right, so that's kind of this, and there are some. So a plane jet basically has certain. It is self-similar, but what what are the salient features of something like this? Okay, so this is statistically 2D. Okay. Dominant direction of mean flow is X, right? Statistical symmetry about plane y is equal to 0. And statistics is independent, statistics is also independent of coordinate z, okay, and statistics independent of coordinate z, okay. Now in an experimental setup, okay, so let me explain that a little more. Right? Okay. Okay, and so this height is d, so you can sort of look at the figure here, so this d, this is the height d, so this is the height d that I'm talking about. Okay, so what I've drawn here is looking at just one section. Right, it's a 2D picture. What I'm trying to draw here is a 3D, okay, and this is W. Let's just say the width. Oh, this is W. Okay, so this is essentially a rectangular nozzle in lab experiments. So this is a okay. So in the sense that when we say that statistically 2D dominant direction of mean flow is X, okay, statistical symmetry about plane y is equal to 0, statistics independent of z. Now I'm saying these things what is that? Why am I saying this? It's because these things define what I'm saying by a plane jet. We had a round jet and now we have a plane jet. So what makes a plane jet plane, and not round? So there is some kind of geometrical symmetry that we're talking about. Okay, so in an experimental setup in a lab, this is what it looks like, right? And so what we have to make sure is that we have a plane jet, right, and it satisfies these geometric parameters, is that the aspect ratio, okay, is W by D, okay, is about 50, or this W, right, the width is at least 50 times the height. Okay, so you can see that about the y-axis, right, about the y-axis, the length is much larger compared to the height, right, in the y direction. So W is about 50 times D. Okay, so that say for z is equal to 0, right, for z is equal to 0, which means that we are looking at this location. Okay. So, otherwise if you need different section, then you come along. So, at z is equal to 0, and for x by w small or not too large, right, which essentially means that it's close to the nozzle. So, x by d, x by w is not too large or small, which essentially means that is close to the nozzle. Okay. So if we have a plate which is about the width is about 50 times the height, right, then at z is equal to 0, right, at z is equal to 0, and for x not too far away from the nozzle, right, the flow is statistically 2D, right, and free of end effects. Okay. So, when I say plane jet, now the point is, what do you mean by plane jet? So, that's when we came up with these conditions. We said these are the conditions which will make a plane jet. So, now the point is, okay, so I go to a lab setup, right, and I know what a plane jet is. I know what conditions have to be met. So, then how do I get to work? How do I do that? How do I set it up? So, this is what we do. So how big the plate is, how long is it, how tall it is, and what exactly are we looking at, So that's the kind of question we try to answer to essentially, have a plane jet. So now we're ready to do the experiments. Okay. Okay, now that this is a plane jet, okay, and we're saying that this is this is a self similar flow. Okay, now so if I do experiments, okay, mean velocity and Reynolds stress profiles, okay, become self similar. Okay, beyond (40). Okay, so yeah, so if I look at a distance, right, so if I look at a distance somewhere along x here, right, so this x is actually greater than 40 times the height or dia of the nozzle. Okay, 40d. So this is the from here, this is the location, right. So this is the place where the mean velocity profile and the Reynolds stress profiles, they become self similar, right. Beyond x by t is 40. Okay. Now if that is true, let's go and look at some experimental results in that effect. Okay, let's go and look at that, and then I'll come back to talk about a few things. Okay, yeah, I think we should do that. Okay, so let us look at this plot first. Okay, so the mean velocity profile in the self similar plane jet, right. So this is from an experimental data of 1965. So you can see here that this is a self similar profile. So f of zeta is nothing but y by y half. right? And what we see here is this symbol basically represents the mean value. This is the centerline velocity. So simply the u bar by u, u naught or u infinity basically, right? That is self-similar. That we can see. This is from experiment. Now then, okay, and if I look at yes, so this is okay, this is self-similar. Yes, now this is the Reynolds stress tensor. Okay, this is the Reynolds stress tensor, and what you can see is that this is very interesting. This is a very interesting plot, and this is again from an experiment in 1965. Okay, so if you see, they've really drawn 3 different parts as the data is represented. Okay, so this one, the square, is basically corresponding to the turbulent kinetic energy in the x direction, right? So we can see that. Then the same thing we see even for v, right? The lateral velocity, which is this, right? And finally, the w square is the velocity, is the kinetic energy in the z direction, right? Now uv on the other hand, these are the Reynolds stresses, right? This is self-similar with zeta, right? So it's essentially, so this is going to be, by if you see by parts, and then this is the total kinetic energy. So this is the ui dash uj dash by u naught square. Okay. So here the mean velocity component as well as the turbulent viscosity, or the Reynolds stress profiles, they become self-similar. Okay. Now going back, we have something called. So now the point is that what is we do have a round jet. Okay, and then what is so we will see how different the plane jet is, right? Okay, so now we saw those 2 plots. Okay, now then let's say so the scaled turbulent viscosity, okay. Okay, and this we can write as okay. So this is the turbulent, this is the viscosity, right? And we are scaling that. We are scaling the turbulent viscosity with the centerline velocity and y half. Okay, so we do that. Okay, now then for S is equal to okay, this is equal to 0.1. Okay, this is from experiment. Okay, S is equal to this, right? Now turbulent RE, okay, is okay, and this is about 31, right? So the turbulent RE, so let us sort of do that. Okay, so the turbulent RE is about 31 for a self-similar plane jet. Okay, now for the round jet, this RET was about 35. Okay, that's just to bring in some comparison. So for the round jet, okay, so RET is about 35. All right. So now that is to give you some idea, right? That's just to give you some idea as to what other type of similar flows are possible, because I think one of the reasons to touch upon this topic is to kind of not forget that although we are harping on an around jet, etc., but the focus is just on turbulence in and around us, right? So there are more than one similar flows available, and we are trying to study a few of them and see if they kind of see if they can kind of give us more inroads into how turbulent flow, turbulent behavior will look like. Okay. All right. So then, now that we've done with that, okay, let's move on to the plane mixing layer. So this is interesting, and here's I'm going to try and explain that a little better, the geometry part. Okay. So now we have a plane. Okay. So the plane mixing layer. Okay, let me draw it and then I will explain. Okay, so okay, okay, so then okay, so let's just say that this velocity is UH and this velocity is U1. Okay, and again we have here the y-axis, okay, and we have a profile, okay, then US okay, and this is the characteristic length delta. Okay, so this curve is essentially for the U mean. Okay, it's for the U mean. Okay. Okay. Now let me sort of write down a few things and so that we understand. Okay. So as you can see, I mean again, what is a mixing layer, right? So what you can see here is I have two fluids, right, which are moving parallelly, but they are not. There's no connection as such between them. It's almost like cars moving on two different lanes of a road. Right. So here too, they're pretty much independent identities. The UH and U1. Okay. Now, so let us see, and then now we call this a mixing layer. So at some point, how do we bring these flows to mix, and that's where the turbulence comes in. Okay. So now mixing layer. Is the turbulent flow okay, that forms between two uniform nearly parallel streams okay, of different velocities. Okay, so UH and U1, right? So which is denoted by UH and U1, okay, and here this. Okay, so this is what we call as a mixing layer. It's basically, you have two independent, right, uniform and yes, more or less parallel streams, right, and these are flowing with each other. These are flowing like adjacent to each other. Okay, and that's why we're saying it's a plane mixing layer, right, and so there is a the velocity, one is big, one is small, etc. All that is there. Okay. Now before I do some, okay, let me first write out the first thing, then we'll say a few things. Okay. So example of this. I mean, where can I find a plane mixing layer? Where do you think I can find it? Is there, does it ring a bell, or is it giving you some ideas? Where do you think I could, see a plane mixing layer? Where do you think I could, see a plane mixing layer? Right? Now think about this. So we have the plane jet, right? So when you see this jet, right? So you see the jet which has come out, and we can write this as, yeah, because that's the jet velocity with which it comes out. Now when it comes out, just look at the picture here. So we have this jet velocity, right? So it's a stream of fluid which is being let out from the nozzle, right? And it's parallel, lines of flow, which is this, right? And it is flowing into, what about the surroundings? The surroundings are basically quiescent, isn't it? So therefore there is no velocity there, but there could be. But as of now, this problem, so this problem, so here we do not have, so we could have, so as it comes here, there I could draw these. Right? So you could actually have another parallel stream of fluid. And yes, that's totally possible. So in here though, it is quiescent, so therefore these values, so this V is actually, it's actually equal to 0. This is quiescent, okay. So if I go here, so I have a UH. So if you want to see this, so then basically what I'm saying is that this, right, so this is my jet, right, so UH is equal to, right, so I can say that UH is jet velocity, right, and U1 is equal to 0. Okay, so this is what I'm trying to say here. Okay, so then again here, the dominant direction of flow is Z, and the statistics independent of Z direction. Okay, so dominant direction of flows is the X, right? Statistics independent of Z. Right. So statistics independent of Z. Okay. So we have two imposed velocities in the plane mixing layer, right? UH and U1, right? In this context, what we can write is that, so now I have this, right? Now when I had the previous one, which was a plane jet, right? U1 was 0. So you can say that plane jet is a special case of the plane mixing layer. Right. So I have jet flow, the flow which is coming out, and it is coming out into another fluid, right, and the fluid adjacent to it is quiescent, it's not moving, right. So that's like a special case of the plane mixing layer. right. Now, plane mixing layer here, so we essentially have two imposed velocities u h and u1, right. Then this is my flow. This is basically my flow. I have a UH and a U1, right. Then if I had to, for example, if I had to calculate Reynolds number now, right. So I will need one velocity, right, and I will need one characteristic density, right, viscosity. How will I do that? Because now if I say that I actually have two of these, which as such are independent of each other, but if I give these values, how will they calculate, right. So velocities. So we defined a characteristic sorry. So what does this mean, characteristic convection velocity? Well, if you have, for example, if you have this here, right, if you look at the plane jet, right, so this is the velocity, so you're calling it uj, right, but if you come here, what will we call this, right, because I have two imposed velocities, one is uh and one is u1, right. So then if I have to define a velocity for the profile, define a velocity for the domain, right, which one should I name, which one should I take, right. So that's when we use this. We basically say characteristic convection velocity because there are two imposed velocities. So that this is essentially UC, right, which is equal to half of this, right, UH and U1. Okay. And characteristic velocity difference, so characteristic velocity difference, so that is actually the US, right, which is equal to this, right. So now you see, so US is actually UH minus U1, okay, U1, and so you could if you look at this velocity profile here, so essentially how do I draw this? So I superimpose, right. So that's what we said. So yeah, so we have two imposed velocities, so you have UH, okay, and then now I have the U1. So then what do I do? So UH, so this is UH, right, and then with that you add the U1, right. So U1, and so you could basically actually I think it would be okay. So if I draw this line here, right, so maybe this is U1, right, and then this is your UH, so you can superimpose that. So now, so this US is basically the difference between the two velocities, and VH was V1 by 2 is equal to UC, which is a characteristic convection velocity, right. So that is that. So then characteristic convection velocity is sum of velocities by 2, right, and the characteristic velocity difference is simply the difference between the two velocities, right. Okay, now the point is that where do we find something like this? Where do we find something like this? Like I just said, at the starting of near the nozzle, at the starting of the flow, right. So which is development of a plane jet. So this is there right at the beginning, right at the initial stages of a plane jet, right. Okay, so now we can look at a couple of plots again, right. So right, okay. Now we have this here. So this is a sketch, right, as you can see, of the mean velocity. Now we are looking at the mean velocity, right. So this is the mean velocity and this is the y, right, and the scaled mean velocity profile, which is here, right, showing the definitions of y at 0.1, 9 and delta. Okay. Now, if you see this, right, so let me draw this here. I have, so if I look at this, okay, now in here, yeah, well, you can see that from here actually. Okay, so let's just say that this point, right, so this point here, right, let's just call that as P, right, and again let's just call this as yeah. Why am I drawing this here? Because there is a change in slope. There is a change in slope at these two locations, and you can sort of see that. Okay, and that. Okay, so there is this. So the way we write this, okay, I'm going to write it out. Okay, is that, and this is the value of zeta, right? This is the value of y at point 1. Okay, so this is the delta. Okay. Although it's actually given here. Okay, so let's sort of look at that. So I can write it here actually. So UP, right, is equal to U1, which is this, right, plus this. Now plus this, how do I do this? So all I've done is that the UH, so UH is this value. Okay, UH minus U1, right, and a fraction of that, depending on where P is located. So P is located by 0.1, so therefore this is 0.1, and hence U1 plus UH minus U1, right, the difference, and the difference, a fraction of the difference, which is 0.1, right. So that's how we get the P here. So similarly we get the Q, right. So again U1, right, plus UH minus U1, and this bit, the distance is basically 0.4 minus 0.5, therefore 0.9. So what we have is U1 plus UH minus U1 into 0.9, right. So that's your Q, and so what is delta, right? So what is delta? The delta basically is y at 0.9 minus y at 0.1. Okay, so this delta is that, you can see that. Y 0.9 is this, right. Now y is the, so what is this y? Y is the height of the flow, right. Y is equal to this thing. If so, y is height flow, okay, this, right. So, and delta x we just wrote down, then reference position, okay. So we take an average value of y is 0.1, so y is 0.9, right, plus 0.1 by 2, right. So that should be our y, so that is the reference position, that is the reference position. Okay, now having done this, okay, now let's see, we have, let's look at the other plot. There you go. So now f of zeta, so this is, now look at this, now this is a scaled velocity profiles in a plane mixing layer, right. So scaled velocity profiles in a plane mixing layer. So symbols experimental data of Champagne et al. Okay, so this is basically shown, this is an experimental data, right, from 1976, and it basically shows that the numerical plot that we had just now, you see, if you see this, this is the velocity plot, okay, so it kind of matches. So this is something that you can see, and of course now let us look at the plot, okay. So now this f of zeta is basically self-similar. Okay. Now, spreading rate, so the spreading rate, okay, so the spreading rate here, so I am going to write this down. So, S is equal to UC by US into d delta dx, and this is constant, right. This is constant. Okay. Let us look at this plot. So, if you see this, so this is the f of zeta. Okay, this is an interesting point. So, now it was kind of obvious, right. I mean, you have a jet and the jet comes out and it spreads. It was kind of almost like intuitive. It is just that we did not understand all the nuances of it, but we kind of knew. So, when the jet comes out, it always spreads like that, right. In this case also these are free shear flows, right. Now, you have two adjacent fluids, right. Now, if they were to travel like this, will there now is there going to be a symmetry, is there going to be is it going to be there, right. So, I think so will it spread, how will it spread, right. So, that was the point. So, now if you see here, this is the actual variation of see y. So, actual variation meaning that now in, so I am moving, so let us go here. So, right. So, now y is the distance in the direction. Now, this y we are calculating. So, this y is something that we have been calculating, right. Now, how this length y will change as we move along x, right. So, that is the point, that is what we are trying to understand here. So, it so happens that the plane jet will spread, right. So, if you see y point, this is three different ones, y 0.95, 0 and y 0.01, right. So, these are the points. So, we do, so x is in centimeters in this plot, right. As well as x increases, so as x increases, you can see the actual variations, right. The actual variations, although we have said that for s is actually constant. Okay. Yeah, well, that is all. I think we will kind of stop here. Okay. So, essentially if I might just round this up a little bit. Okay. So, this is the spread that we are looking at. Okay. And when I look at the self similarity, I am basically looking at the f here, the mean velocity, right, by central line velocity, that is that is self similar. Okay. So, this is what it means, in terms of when we did the round jet, then we did the jet half width, right. Now, if you have two fluids like this, which essentially I am talking about the plane mixing layer, right. You have two fluids, two different velocities, right. Now, what will happen then? What will happen to the jet? Okay. So, I think that is something we try to understand. We will take up something else in the next class. Okay. So, thank you. I will stop for now.